Hi and welcome to this IB Maths Intense video, fifth video about sequences and series, and in this video we'll be looking at geometric series, following on from the work we did in the last video on geometric sequences. Now, as you'll remember from earlier videos, a series is the sum of a particular part of a sequence, so a particular number of terms. And these examples that are on this particular slide, they're all examples where we've taken 5 terms from a geometric sequence and we're interested in their sum. So if I was using sigma notation, for example, this first one I would write as the sum of terms n equals 1 to 5 of the sequence 2 to the n minus 1. I won't write all the other ones, that's fairly straightforward. But we're interested in the sum of a particular part of a geometric sequence, as we saw with our arithmetic series before. How do we find the formula for the sum of a geometric series? Now, this is a little bit more difficult than when we were finding the formula for an arithmetic series, but let's have a go. Bear with me. This first example then, we've got a series. It starts with 2 and has a common ratio of 3. We're multiplying by 3 every go. So let's just write down what we know. U1 equals 2 and the common ratio equals 3. Now, what I'm going to do is something a bit strange here. I'm going to multiply the whole of that series by the common ratio 3. So I'm going to create RS, in other words 3S. So I'll write that underneath. And that is equal to, let's multiply everything there by 3, and you'll see that we just get a very similar pattern to the one above, just shifted by 1. But we need an next term at the end, which is 3 lots of 162, which is 486. Now I'm going to subtract the top line from the bottom. So 3s take away s gives me 2s. But in other words, it gives me r minus 1 lots of s, where r is 3 minus 1, so 2s if you like. So this time I'm subtracting, 6 take away 2, I get 4, then I get 12, then I get 36, then 108, and then finally I get 324. And if I add all of those up, I get the total of 484. Now that doesn't look anything interesting. R minus 1s is equal to 484. But where does that 484 come from? It's this 486 from the end of this particular series, subtract 2 from the beginning of this. So what do those relate to? Well, remember this term here is U1, and this term here is derived by U1 r to the n minus 1. So this term here must have been U1 times r to the n, because we've multiplied 162 by 3 again. So 484 is equal to 486 minus 2, which is equal to U1 r to the n minus U1. So what have we got? Well, we know that this bit, r minus 1 lots of s, equals U1 r to the n minus U1. So let's see what that gives us. R minus 1 lots of the sum equals U1 r to the n minus U1. Let's rearrange that. Sum equals, I can factorize this as well, U1 r to the n minus 1 all over r minus 1. And that is our formula for the sum of a series. In fact, there is a second version of that formula. We can also write things the other way around. 1 minus r to the n and 1 minus r. They both give exactly the same result. We can't use either of these where r is equal to 1. So r can't equal 1 because we can't divide by 0. And this particular version of the formula we tend to use when r is greater than 1, because the maths is easier. R to the n minus 1 is easier when r is greater than 1, and this one here we tend to use when r is less than 1, because the maths again is going to be easier. And sure enough, if you look at the formula sheet, there they are. Those are those two versions given for you. You don't need to remember them. And the simple questions just utilising the formula are very straightforward. So in this example that I've put up for you here, 1, 2, 4, 8, 16, the first term is equal to 1 and the common ratio is 2. I'm doubling every time. It's always good just to write down what you know so that you can plug it into the formula easily. So the sum of these 5 terms that I've got here, I'm just going to get by multiplying 1 by, well, I'm going to use the first formula because r is greater than 1. So it'll be 2 to the 5 minus 1 all over r minus 1, which is 2 minus 1. So I end up with 2 to the 5 minus 1, which gives me the ground result of 31. Very simple way of finding the sum. Of course, you could have added those up yourself in your head, but this is really just for purposes of showing you how the formula works. Let's look at another question. A geometric series has first term 10. Let's write that down. U1 equals 10. Common ratio equals 2. Find the sum of the first 8 terms. So again, I don't need to know the formula for the nth term. I've got everything I need to work this out. S of 8. Let's just plug these into the right formula. We're going to use the first one again because r is greater than 1. 10 times r to the 8. That's 2 to the 8 minus 1 all over 2 minus 1, which is going to give me 10 times 255, 10 to the 8, 2 to the 8 minus 1, 256 minus 1, and that gives me a total of 2550. Again, very simple and straightforward to work out the total there. You might see a question that is using sigma notation here. So no panic here, just write down what you know. You know that the common ratio is equal to a half, because I'm multiplying 3 by a half to the power of something every time. So common ratio must be a half. And my first term, I need to take care here. I need to plug in what I've got in this this notation. When r equals 1, the first term would be 3 times a half to the 1. So 3 times a half is 3 over 2. So my first term is 3 over 2. Just be a little bit careful with that you calculate the first term correctly. And then we can just plug that nicely into the formula. Sum of the first 10 terms, we want first 10 terms, is given by 3 over 2 times. I'm going to use the second formula here because r is less than 1. So I'd end up with 1 minus a half to the power of 10 all over a half. And then that's 1 minus half. If I work that out on my calculator, I get 2.9971 to 4 decimal places. Now, remember this result because we'll come back to this later when we look at convergent series in the next video. We might have to work backwards in some way. We're told the sum of the first n terms of a geometric sequence is given by Sn equals 10 to the n minus 1. Find the first term and the common ratio. So we need to use a bit of lateral thinking here. The first term will also be the same as the sum of the first term, won't it? So we can work out S1 equals 10 to the 1 minus 1, which is 9. So the first term, U1, must equal 9. The sum of the first 2 terms is going to be 10 squared minus 1, which equals 99. So the common ratio, R, is the second term divided by the first term. So if the sum of the first 2 terms is 99, then my second term must be equal to 99, subtract the value of the first term, which was 9. So my second term must be equal to 90. So my common ratio will just be 90 divided by 9, which is equal to 10. So I've answered the question there. The first term is 9 and the common ratio is 10. And I was able to derive that information just by thinking about how the sum was made up. Okay, often with this geometric series, you'll get what I like to call wordy questions. So you need to pull out of that what really is the geometric sequence or series. This question says, a woman lives 400 metres from her place of work. She walks 100 metres in the first minute, and in each subsequent minute she walks 80% of the distance she walked in the previous minute. Show that she takes between 7 and 8 minutes to walk to work. Well, again, let's write down what we know. We know the first term, the first amount of distance that she walks is 100 metres in the first minute. And in the second minute, she's going to walk 80% of the distance she walked. She's going to walk, 80 metres. U2 is equal to 80. So that means my common ratio is 80 over 100, which is 0.8. In other words, 80% of the distance. So we can now work out, because we've got R and U1, how much she would have walked in 7 minutes and how much she would have walked in 8 minutes. And we can hopefully prove that she will have arrived somewhere between those two times in her workplace, which is 400 metres. So the sum of 7 terms is equal to 100, because that's my value of U1. And I'm going to use the second formula here because R is less than 1. 1 minus 0.8 to the power of 7, all over 1 minus 0.8, which is 0.2. And if I multiply all that out, I end up with 395.14 metres. So she's not quite reached her place of work after 7 minutes. So let's just prove that she's reached it by 8 minutes. 100, 1 minus 0.8, this time to the power of 8, all over 0.2. And this time we'll find, yep, sure enough, if we work that out on your calculator, you'll see it comes to 416.11 metres. So we've proved takes longer than 7, but less than 8. There we go, proved it. Last is just to show you that our favourite solving method when working with exponentials, i.e. logs, is also useful when we're working with geometric series. So this time we're told how many terms are needed, in other words n, for the sum of a geometric series 1, 2, 4, 8, 16, one that we saw earlier, plus 32, etc., to exceed 100,000. So we've got, again, information that we know. U1 is equal to 1 and the common ratio equals 2, and we're looking for the sum of n terms, and that's going to be 1 times 2 to the n minus 1 over 2 minus 1, which is equal to 2 to the n minus 1. Now we want that to be greater than 100,000, so we want 2 to the n minus 1 greater than 100,000. In other words, 2 to the n greater than 99,999. And then we can take logs. So n log 2 greater than log of 99,999. Rearrange n greater than log 99,999 over log 2, which gives me n greater than 16.6. So how many terms are needed to exceed that? Well, 16.6 terms, we can't have 16.6 terms. 16 terms wouldn't be enough. So 17 terms are needed. So there you go. There's just a mixed bag of questions relating to geometric series. There are lots of other flavours, and hopefully in the course of other videos I'll have the opportunity to show you some more questions around solving geometric series. But for now, thank you for watching. I hope that was useful. Don't forget to like this video, subscribe to my YouTube channel, IB Maths Intense, tell your friends I'm here, and send me an email on ibmathsintense@gmail.com if you've got any queries, any requests, or anything else you want to see. Look out for the next video, which builds on what we've done on geometric series and looks at infinite geometric series, which uses the similar sort of formula, but we'll go into a little bit more detail on that. Anyway, in the meantime, you take care and enjoy your maths.